right, so let's get started today. It's my pleasure to introduce Pieter Abbeel. Peter's visiting us from Berkeley and OpenAI. He's been a professor at Berkeley since 2008. And he's been spending most of his time these days at OpenAI. He has won a huge number of awards. Some of the ones they noticed were President for the Career Award, the MIT Tech Review, Top 35, 135, lots of others. He works in an area that I'm sure a lot of you have heard about, deep reinforcement learning. That is taking the world by storm these days, the deep learning world. And he's worked on all kinds of interesting applications. So a wide range of things around doing helicopter acrobatics and learning how to do that, learning how to pick up and fold laundry, and also lots on surgical robotics. So all kinds of interesting applications. So yeah, Pieter's visiting us here today. Welcome.
Thank you, Rich. So one very quick pitch I want to make before I start. I even have a third affiliation. It's called Scope. And if you ever have to grade homework or exams and you wish you were spending less time on it, check it out. It'll help you drastically reduce the amount of time you spend on grading. Your teaching assistants can do research instead of grading. So yeah, check it out or email me and I can make sure you get set up with an account quickly. It actually has AI too, or it's getting AI built into it as we speak to hopefully fully automate grading for you, which would be ideal. All right, so I'll talk about some of the work we've been doing at OpenAI and Berkeley. And let me start with introducing the framework under which we're doing this work, or most of the work. So what we're interested in is having a robot act in an environment. Based on the current situation, your AI agent software is supposed to decide what to do. So you have a policy, pi theta, which decides on a distribution over actions given state. Picks an action, action gets executed. Then the world changes and the cycle repeats, okay? And what we want to do here is maximize expected reward. So the objective is, let's say in a video game, maximize score, which would be reward in a video game, or let's say you have a robot that you want to cook for you. Maybe the robot cooks, brings you a meal, and then you give it a rating from 1 to 5, and hopefully over time it figures out how to get 5-star rating, and that's amount of stars is the reward. Now, there's not just applications in robotics. This has applications in a lot of other domains. Marketing and advertising, where if you build up a enduring relationship with a customer, you have a higher chance of success. Dialogue, then in dialogue, this here would be the mental state of the person you're conversing with, and that mental state would change. And based on that, you need to adjust your actions to try to get that mental state somewhere. You might want to optimize operations, logistics, power management, and so forth. Compared to supervised learning, if you wanted to solve this problem with supervised learning, what you would do is you would have somebody act, and then you would try to learn a mapping from situation to action. But that's not what we're going to do here. We want to optimize directly the objective we care about, which is expected reward. And this brings new challenges. So because of the feedback loop, one new challenge is stability. If you naively just run supervised learning, learned an action that is maybe more or less the right action, what will happen is after taking that action, you will be in a situation that's actually slightly different from what your expert demonstrator would have seen, and you'll be out of the training data distribution by just a little bit. And as a consequence, though, you would then have a harder time making the decision, and then this could destabilize over time. So the temporal effect here, the fact that you affect the world, makes it very different from just trying to match actions. Credit assignment is a big challenge. Imagine you have the robot, and the robot cooks for you. It's busy for half an hour in your kitchen, comes out, and you give it a rating. That's very little data. For a half an hour of work, it's very hard for the robot to understand what it should change about what it did from just that one data point. Of course, it can go again, cook again for a half hour, give you a meal again, and now it can maybe try to tease apart. One was 5-star, one was 4-star, what was different? Doing that teasing apart, that's the credit assignment problem. Understanding what it is that mattered to increase reward or decrease reward. A third big challenge is exploration. the system has to do things it's never done before. It has to invent new things that somehow are good to maximize reward. Because if it already knew what to do, there wouldn't be any learning anymore. And so you wanted to somehow figure out what are the right actions to take such that it experienced something meaningful it hasn't done yet, and then hopefully learn from that. These three things make reinforcement learning a very hard problem. Despite these challenges, though, there have been quite a few successes recently. One major success you might all be familiar with is the success on Atari. The first major success here was in 2013 out of DeepMind. And what happened here is they were able to train a deep neural net. In fact, the deep neural net architected much like AlexNet, the first deep neural net to be successful on ImageNet. But instead of outputting an activation for cat versus dog, car, and so forth, it would output an activation for each possible joystick action. It's still raw pixels, and it collects its own data, learns from its own experience what the weights in the neural net should be, such that the neural net becomes a good neural net at predicting actions that lead to high reward, that is high score in the game. And the beauty here is you can run the same algorithm on different games, and it'll learn to play a wide range of games from scratch. What I've been interested in a lot is how to make this happen for continuous systems, like robots. So, for example, could we get this simulated robot to learn locomotion? And ideally, could we make it learn locomotion from a very simple description of what the task is? So let's say the description is as simple as the further north, the better, the less impact with the ground, the better, and the lower torques, the better. So just 3 components in what we care about, and that's it. No data about what walking looks like, running looks like, or anything like that. Can we have the system learn to control itself from its own trial and error? In fact, this is now possible. And what you'll see here when the video plays is a policy gradient method in action, TRPO, using generalized advantage estimation to estimate the value functions, the advantages. And what you'll see is initially, the neural net is initialized randomly, so what you expect is the robot will just fall over. But then, from repeatedly falling over and having some randomness in the falling over behavior, it'll start teasing apart what makes a difference in terms of maybe falling over a little later rather than a little sooner, update its parameters, and then do a little better in the next iteration. And over time, it invents something that actually optimizes reward. So what you see here is iteration 40, it's doing a little better, falls over after a half second instead of immediately. Iteration 160, it actually starts making some progress. It invents a gate that allows it to get further north, have lower impact with the ground, and relatively low torques. Now, of course, I'm not showing every rollout here. In practice, there is many rollouts per iteration. There's, I think, a few thousand rollouts per iteration, and then there's an update, and this repeats. But after 2,000 iterations, which in real time would be about 2 weeks of training time, but of course, simulation is faster than real time and can be parallelized, it actually invents locomotion. Here, exact same algorithm, no change, just a different simulator. And over time, it also learns to optimize, again, same reward, minimizing torques, minimizing impact with the ground, and maximizing progress in the north direction, and invents actually a really, really fast gate for 4-legged locomotion. If you look at it carefully, you'll see it does something pretty amazing that probably no real robot could do, but it optimizes reward in this simulator. What you see here is same algorithm, but the reward function is distance to standing head height. The closer to standing head height, the higher the reward. And so over time, it figures out that there is a way to map from joint angles, joint velocities, and the location of the center of mass of the robot to torques at each of the motors to get the robot to get very close to the desired standing head height. Now, this is a simulation. You might say, well, 2 weeks is not too bad. You can put it on a real robot, but of course, that's not how research tends to work. If we were to put this on a real robot, it's most likely it wouldn't work because some hyperparameters are wrong. Maybe the entire architecture isn't exactly right for the real robot. And so 2 weeks is probably pushing it to be able to run on a real robot. So something we did is actually we came up with a slightly different approach to get some of these things working on a real robot, something called guided policy search. And what we looked at here is, can we learn more quickly by making 2 additional assumptions? what are the two additional assumptions we were willing to make? Assumption one, the ability to reset. So you can reset your robot into the same initial state if you want to. If you're able to reset, you're in a simpler problem because often the solution to your problem now can be just a path in space. It doesn't need to be as complicated a feedback controller. And those might be quicker to find than something that is good for the entire space. So that's one. So we're going to run reinforcement learning now for very specific situations rather than a wide range of situations. Now, to still have it generalize, we'll solve it for several specific situations. In this case, in the video, you'll see we'll solve it for 5 specific situations. And then we'll train a neural net to match up with those behaviors that we see in those 5 specific situations. And then the neural net will generalize to new situations from that. Okay? The second thing that we do differently, rather than learning directly from pixels to actions, which requires learning something quite high dimensional, which can be tricky to learn, we learn from motor angles and velocities to motor torques. When we learn the specific controllers, so to get our 5 successes, but then when we train the neural net that needs to generalize, we train from pixels to motor torques such that it matches up with what the trajectory-specific controllers have learned. And so what you see here in action is one of those trajectory-specific controllers that is learning to place the block over here. And so this takes about 10 minutes. And once you do then, when you do this for multiple different locations, it'll each take 10 minutes. You can train a neural net on top of that that agrees with all of those, that goes from just pixels to actions and succeeds at, in this case, block stacking. And so total time would be about an hour now to train a skill rather than 2 weeks. It's a more confined skill than the simulated locomotion, but it's possible to train it relatively quickly. We actually applied this same idea to tensegrity robotics. This is the NASA Super Bowl. It's a robot that's built for planetary exploration. The idea here is that you can this is 6 bars and 24 elastic cables. If you pull the cables, it'll change shape. It's resting on a triangular support surface. If you pull cables, then that triangular support surface will change shape, and the center of gravity of the robot might shift outside of that triangle, and then it'll tumble over, and you can repeat this and get this robot to move somewhere. You can also compress it, and so it's extremely volume efficient in terms of shipping robots somewhere. It can also take impacts well.
Just a clarification question on the earlier one.
Sure.
So when you were mapping through
The neural net to go from pixels to action, reinforcing it to go through the angle, or was it really just matching to action? You did have to order control robots.
Okay, yeah, so when we go from pixels to actions here, matching up with what the motor angles and velocities to actions were for the specific controllers and matching that to then generalize to new situations from vision. The network takes in pixels, processes them through a few conv layers. Then at some point, it also takes in joint angles and joint velocities of the robot. And where that comes in, there's actually a special layer that is a softmax layer that essentially localizes. In this case, there's 32 channels. So for the 32 feature channels, it localizes where each feature is most active and passes on 32 pairs of coordinates, 32 pairs of image coordinates, as well as joint angles and joint velocities to a few fully connected layers that then decide on the motor torques. But we don't force those things to have a particular meaning. It picks up on whatever features are relevant to localize to then be able to do the right thing. So I didn't show in this video here, but there's an example where the robot's holding a hammer, supposed to get the claw of the hammer underneath the nail. And so there it has to pick up on understanding where the nail is and understanding how it's holding the hammer, because the combination of both will determine what the right motion is. You can pre-train by outputting some pose information at that level, and it speeds things up. It's not clear it's actually needed, but it does speed up the training. So you can initially move your robot around and pre-train on pose estimation. Any other questions? Not for now. So this robot, NASA is trying to get deployed in the future to do planetary exploration. The challenge has been to actually do locomotion with this. They've been able to design controls that can make it tumble from one phase to another phase, but not continuously roll. And so what we've been doing is using this trajectory controller, optimization, and then a neural net on top of that to generalize to actually get this kind of result here. So what you see here is the first successful continuous rolling of this tensegrity robot, the Super Bowl. This is at the NASA Ames Center, and moving much better than they were able to make it move before we collaborated with them on getting this approach running on their robot. The interesting thing here is that actually we were able to do this by training purely in simulation. They had a pretty good simulator that captured the dynamics of this robot quite well. And so by training in simulation, with some tricks in terms of introducing a lot of noise in the simulation and a lot of variations, so training against multiple possible settings of mass, properties, and spring constants and so forth, then it's possible to deploy it on the real robot without any new training on the real robot. So these are some success stories in control. In game playing, of course, there's AlphaGo from not too long ago from DeepMind. And so I think there's been a lot of success in the domain of reinforcement learning, but I think there are still many, many challenges. And I want to tell a little bit about some of these challenges. I think the first big one is sample complexity. Almost all the successes require a lot of data. And so the question is, can this be brought down? Another one is safety. And so among sample complexity, there are 4 thrusts that I want to tell you a little bit about that we've been working on over the past year. First one is RL squared. It's hard to explain briefly, so I'll just defer that to when we talk about it. Second one is algorithmic priors, how to build in knowledge we have about what the neural net should compute into the neural net, yet still have the flexibility that it provides in terms of adapting to raw sensory information. Unsupervised learning as the kind of premise of speeding up all kinds of learning. Not claiming we've managed to make it speed up reinforcement learning yet, but I want to tell you about some ideas that maybe in the future could contribute to that. And then imitation, and especially third-person imitation learning, I think will be really important to get robots in the world where you learn from watching people, watching YouTube videos, rather than learning everything from scratch. But the big challenge here is to learn it not from seeing things from the robot's point of view and doing it yourself, but learning from somebody else doing it and understanding how to map that to your own executions. So let's start with RL squared. Let's look at the success on Pong. So let's look at DQN, which is a DeepMind algorithm. DQN versus humans. Okay? DQN's average score back in the initial results was 18.9. These days it's 21.0, which is the max you can possibly get. And the human score is 9.3 for the human they compared with, which is a human that got, some practice on this game and then see how well they do. So the computer is doing twice as well as the human, if you measure this way. But then if you measure in terms of experience, in real time, it takes the computer 40 days to learn to play, whereas a human takes just 2 hours to get to this performance. So it's reasonable to say that DQN is slow learning relative to a human, which is doing fast learning. And so the question is, can we get to the faster learning? The starting observation for us is that the state-of-the-art algorithms, TRPO, DQN, A3C, are fully general. You can present any markov decision process to it. An MDP, markov decision process, is dynamics and reward situations. Present any to it, and it is applicable. You can run it. There's no limitations. However, if you look at the real world, what you encounter there has a lot more structure than anything you could define mathematically. And so the question is, could we maybe leverage the fact that we don't need general learners? We need learners that are good against what are realistic situations. And maybe that way make them a lot faster than learners that try to be fully general. Okay, so first question then would be, how do we acquire a good prior for real-world MDPs? Or maybe initially for real games. Okay? And then second question would be how to design algorithms that make use of such prior information. Because once you have the prior, it doesn't mean you know how to use it. Maybe many ways to do this. I think it'll be critical to get RL algorithms to work faster than they're working right now. I'm just going to propose one approach to this, but certainly there will be many other approaches, and no reason to believe that what I'm going to present is going to be the ultimate winning approach. But the key idea for our approach is to try to learn a fast algorithm that encodes this prior in the following setting. We assume we're given a distribution over MDPs. So if you're interested in learning to play games, maybe you collect a few thousand games and say that's a distribution that we're going to be faced with. Train the fast algorithm to be fast on a subset of those, which you call a training set. So in typical RL, you would have an MDP, it's fixed, you train on it, and then you act in it again. That's what you would call testing. It's different here. You would have different MDPs. Some of them are training MDPs, some of them are test MDPs. And so you train on the training MDPs. You can't just use the policy you find there, but you hope that whatever you learn there has something you can transfer over to learn more quickly in the new situation. So the representation we're going to use is a recurrent neural net. Just think of it as a generic compute architecture. It doesn't need to be an RNN. It could probably be something else, but it's a convenient generic compute architecture that can compute essentially anything. If you change the weights in the recurrent neural net, it's going to change the algorithm. Okay? And so the hope is that we can train the recurrent neural net to acquire a set of weights such that the recurrent neural net encodes a really fast reinforcement learning algorithm. And then when you run the recurrent neural net in an environment, the activations will change, and that is effectively the policy. You're changing the policy, making it specific to the situation that you're in, that particular MDP. So it's a different way of representing policies. So here's what the training setup would look like. Again, unlike traditional reinforcement learning, we'll be faced with a sequence of MDPs. We'll be in MDP1, then MDP2, then MDP3, and so forth. And the goal here is that if you're faced with a new MDP, and you know you get 2 episodes to act in that world, that you optimize the reward you collect over those 2 episodes. Okay? So you can imagine if it was really just 2 episodes, the first one would do a lot of exploration, the second one would do a lot of exploitation to exploit what it learned in the first episode. And so you would get your agent, drop it in the first MDP, it would act for a while, then it would get reset, and the hidden state would be retained, so it gets to remember things from what happened in that first episode and gets to act the second episode, and then it goes to the next MDP. And from MDP to MDP, it retains things in the weights. So the weights get retained across all of it, and the activations within MDP. So pictorially, what it looks like is a classical RL algorithm would operate on the outside of your policy. It would consider a policy that's taking actions, taking observations, and going through the cycle. Then your algorithm that lives away from your policy would look at what the reward is, and based on that, affect the weights in the policy over time. Here, the RNN policy takes actions, gets observations, which determine actions, but also gets reward, and based on the reward, also does updates to the activations here and allow it to adapt to the situation it's in and hopefully do better. So this is very different here, that this policy knows about the rewards that are happening. And then on the outside, there's a slow reinforcement learning algorithm that updates the weights of the RNN. That says I'm going to change the weights such that this recurrent policy is better at acting in new environments. An alternative view is to think of it as we're going to design a recurrent neural net policy that is good at acting in partially observable Markov decision processes. A partially observable Markov decision process is one where you don't know the full state information. And so that would be the case here. You get dropped in a new game. You don't understand even what the state is of the game. You don't even know the rules of the game yet. You get dropped in a new situation. That makes it partially observable. You don't know which MDP you're in. And you learn a policy that acts in a partially observable environment. Okay? When it's partially observable, you need a recurrent neural net because otherwise you can't retain information from the past to kind of accumulate information and do the right thing in the future.
Another way to do it will be rapidly changing weights of training classes, so to get this extra information.
Absolutely. So I think that would be very interesting to explore. So the fast weights idea, there was a paper you wrote about it just last year. is extremely related to this, and we've been thinking about that. We haven't done experiments with that, but it's an extremely similar idea where here we're saying we'll have the activations encode things, and maybe you could have a non-recurrent policy here, and instead allow this here to update, do the fast wait updates, and have this guy only do the slow wait updates. It would be very interesting to try and see what happens. Actually, quite a bit of related work, because we're now falling in the context of meta-learning. There's been quite a bit of work on meta-learning, not so specific to reinforcement learning, though one of the papers actually is very specific to reinforcement learning. The top one, Learning to Reinforcement Learn, is simultaneous work from DeepMind with our work that I'm presenting here. Intriguingly, I will present to you 3 sets of experiments, completely independently, that shows the exact same 3 sets of experiments. So I guess somehow it was in the air that this was something to try, to think about, to work on. It's not an identical paper word for word, but the high level is quite strikingly similar. The other ones are more on learning for optimization and learning for supervised learning, or meta-learning for supervised learning. So now let's evaluate this idea. So a very simple scenario for reinforcement learning is the Multiarmed Bandit problem. What you have here is a agent is sitting in front of a bunch of bandits, slot machines, and in this case 5 slot machines, and the agent can decide to pull one of those 5. Then there might be a payoff or not, and the agent can go again. Another one of those 5 or the same one, repeat over and over. To make it interesting, there's a different probability of payoff for each of the 5 bandits, and you don't know what the probabilities are. So a good strategy would be something along the lines of, let's pull all of the arms a few times, see which one paid off more often, maybe pulled out one more, but also still pull the other ones a little bit to make sure we didn't miss something important, that I wasn't just unlucky on one of them, and now I realize it actually is a good one. That would be a heuristic strategy to solve this kind of problem. You can also mathematically try to formalize this. You can have a Bayesian optimal strategy in that situation, and that's based on fitness indices. Humans have come up with this. Humans have designed these strategies and have also designed strategies that are close to Bayesian optimal, but faster to compute and maybe easier to generalize to not such a simple setting. And so what we wanted to do here is compare. Compare RL squared, which does the meta-learning and invents the reinforcement learning algorithm, where it would be faced with a set of bandits, episode 1, episode 2, then faced with a new MDP, which means a new set of bandits, go again and so forth. And the question is, how does the meta-learning compare to the human best algorithms? And so if you look at the table here, Gittins indices, which is Bayes optimal, is always winning out, but actually RL squared is almost always winning out too, showing that it is possible to learn a strategy inside the recurrent neural net that is as good, at least for not super long horizons, as good as the Bayes optimal strategy that humans came up with through a lot of research. Here are the learning curves. So the Bayes optimal strategy doesn't have to learn. I mean, people have invented what it is. That's the dashed line. And actually, sometimes it even exceeds because it's Bayes optimal asymptotically. But if you run for shorter amounts of time, then you can actually do better than the Bayes optimal that assumes you're going to go forever. On the longer horizon cases, though, it doesn't fully get there when there's a lot of bandits. Maybe needs more training time, not clear yet. You can do the same thing for small market decision processes. You can say in tiny MDPs, which is, let's say, 2, 3, 4, 5 states, you can run Bayes optimal algorithms, or very close to that, see how well they do, and then compare that with the learning to learn approach and see how they match up. And again here, actually, RL squared, which is the last column, does quite comparably to the best known approach, close to Bayes optimal here, and often better than many of the approximations to that. And here are some of the learning curves in terms of how fast it gets there. The real question, of course, ultimately is, can it solve problems that are so difficult we cannot design the Bayes optimal strategies? And so an example could be first-person view-based maze navigation. Can you have an agent that takes in pixels, gets to take steering actions, and doesn't know a map, but could be in a maze like this, or in a maze like this? The red box would be the goal state. Can it learn to walk around, not walk, but navigate around based on vision and low-level control and get to a goal state? And then when it gets dropped in the same maze again, will it be more effective the second time around because maybe in its activations, or if you re-architected it in the fast waits, it would have remembered things from the first episode in that maze and be quicker at doing the right thing. It turns out it's possible to do this. So before learning, this is what happens. It'll just be a random walk, mostly staring at walls, but then sometimes it turns away from a wall and it actually gets going somewhere. That's before learning. After you train the RNN to encode a fast reinforcement learning algorithm, that's quite specific. It's a fast reinforcement learning algorithm for mazes where the visuals tend to look like this and where the layouts are probably somewhat similar to whatever was available at training time. You get the behavior on the right. This is actually what you hope for. It's very effectively exploring that maze. Doesn't know where to go, it doesn't have the map, but then when it sees it, it goes to it. And then when it gets dropped in the same maze again, for now in these results, it gets dropped in the same starting state, so it's not just anywhere that it gets redropped. It knows that it can compute a shortcut and get to this goal much faster than the first time around. Here are some of the learning curves. What's somewhat interesting here is that it doesn't always succeed. So this is actually not that easy to get to work. About half the random seeds initializations lead to successful learning, and half of them, well, it doesn't do completely nothing, but it doesn't get very far. Longer term, the idea here is to think about how to scale this up to incorporate lots and lots of games. Once you have a wide variety of games, then the hope would be you train on 10,000 games, you try in the 10,001st game, and it would learn to play in 2 hours, maybe even faster rather than 40 hours. Okay, so that's one way to reduce sample complexity. Another way to reduce it is by just knowing what should be happening. If you have algorithmic priors about what should be happening, maybe you can build them in. For example, if you have a navigation problem, you start the red dot, that's your robot, needs to get over here at the pole, and in this case, it has a map. Then a clever way to go there would be to think about the sequences of your action, the consequences of your actions, simulate them in your head, understand that there's a path, and then follow the path. And so if your system understands the notion of planning, it should be able to learn more quickly how to navigate a maze that it's given as an image than when it doesn't know about planning. And so value iteration networks, which was a NIPS paper this past December, looks at that. So value iteration is a standard planning approach for Markov decision processes. If you're not familiar with it, the main thing to keep in mind is just it's a standard algorithm that you can run to plan if you know the dynamics and you know the reward function. And if you use it and you know dynamics and reward function, it'll spit out the right thing to do. In fact, what it'll spit out for every state is how good that state is. And once you know that, you can check from your current state where you can go to, and your policy can then, based on that, pick which action to take, namely the one that goes to the best next state. And so you can imagine if you had value iteration running, it would spit out as D star, the optimal value for each state. You have an attention model based on your current state about what values to pay attention to, and then a reactive policy based on the attention model, and maybe some raw observations to get or tell you what action to take. Now, you can say, well, we could do that, yes, and then if we don't have reward and dynamics model, RNP, we could just learn them from data, collect data. But the tricky part here is that usually your reward and dynamics model will be broken. They will not be exact, and this will not work very well. So we rather do than training those separately, we're going to train them end-to-end. So we're going to train this system, and remember, here is a huge block of computation living over there. It's a planner. We want to train this end-to-end, where we take in images, output actions, and we look either at demonstrations, and we want to match them, or we do it in a reinforcement learning setting. Both can work. And so what we have here now is a very special kind of neural net, where the input is raw pixels still, but then the architecture underneath ends up being something that can do some raw image processing, followed by somehow feeding in reward and dynamics model, which it doesn't know what it is, but whatever it feeds in there will be used as if it were a reward and dynamics model. And by doing that, this part here will be forced to turn into image processing that outputs reward and dynamics model that are useful for planning, such that the planner gives you the right result. And so now, very little has to be learned compared to if you were to learn everything from scratch. So we have an end-to-end differentiable planner all the way from pixels to actions. And so here are some examples. We compare this with a convnet. A convnet would be a generic neural net that is very similar in architecture, but doesn't have the specifics of planning built into it. And you can see that it doesn't, on the reasonable amounts of data that we looked at, it doesn't do nearly as well as using this particular architecture that understands the notion of planning and hence can learn a lot more efficiently. This can be the simple grid world tasks. We also used navigation based on raw images, where we also have height maps corresponding to those images. And so you get an image, the height map will determine how hard it is to navigate, but you don't have direct access to that. It just determines speed of navigation through that part of the space. And you can do continuous control problems too, like this one over here. This idea is not, we're not the only ones pushing this idea, actually, and there's a really interesting extension that came out recently out of Jitendra Malik's group, and here's a video of that in action. What they did here is they said, instead of having an overhead map, the robot gets to see a first-person view. The first-person view gets processed by a neural net, a recurrent neural net, that has space to store something like a map, because you know that a map is going to be useful when you're navigating buildings. So it'll put it into a map. This map is the real map. This is not the map it's constructing. This is just for our reference to know where it is in the building. You take raw images, you turn it into something that has the architecture of what a map could be, but you don't force it to be a map. You don't say, is this a correct map or not? You then use that, feed it into a valuation network, which uses that to choose actions. And so you have a deep architecture here where a lot of it is handcrafted to relate to planning and mapping, but also is matched up through learning with raw pixel processing, which is really hard to handcraft, and also can output raw actions at the end. And so this has been used to do first-person-based navigation in previously unknown environments after training on a lot of environments with humans steering it around and understanding what the right actions are for various situations. The most closely related work to valuation networks is the embed to control work. What they did is they said, rather than going from raw percepts to a valuation block, let's go from raw percepts to a linear quadratic regulator block, LQR. LQR is a standard control approach that works really, really well for linear systems. And so by putting that block there, what you're saying, I need to embed whatever world I'm looking at into a new space where a linear system is a good approximation, and then I can design a controller there and take good actions. And then the hindsight MPC also looks to leverage a LQR, but now in a multiplicative control setting rather than just the single linear system setting. It's also been looked at in estimation. Works at the bottom, but also a lot of other interesting work where estimation has a lot of good algorithms like particle filters, Kalman filters. You know that those do something you might care about, and by hooking up neural nets to the raw pixels, feeding their output into a Kalman filter, you force the neural net to output something that's meaningful for a Kalman filter to work with, like observations of underlying state. Even without you necessarily defining what state is, it just knows that there will be some matrix operations happening, and somehow, if you feed it in state, these matrix operations will be meaningful, and so it's forced to do that. Sorry, something weird happened here. This is the same thing again. Okay. Let me skip through that repeat. Another way to reduce the amount of data you need would be unsupervised learning. As I said, we don't have a good solution, at least not one I'm aware of, that can do unsupervised learning and RL together in a way that really speeds up RL. But here's an idea that we've been thinking about that I think is worth kind of being aware of. One of the big breakthroughs in unsupervised learning recently has been generative adversarial networks. The idea here is that you're trying to generate images that look like real images. Now, the way it's going to work is your system, your deep neural net, generates an image starting from some noise. So you have noise. If you change the noise, then your neural net will generate a different image. So rather than going from image to label, it goes from noise to image. After generated the image, the question is it a realistic image or not? If it's not, you want to know, and you want to change your generator to adjust and become more realistic in terms of image generation. And so a discriminator is looking at the result of the generator and deciding whether or not it looks like a real image. The discriminator doesn't know whether it's getting a real image or a generated image. So sometimes it's actual data, sometimes it's this generated image, tries to distinguish. And so there's a game going on between the discriminator and the generator, trying to figure out, and once you actually reach an equilibrium, what will happen is the generator generates realistic-looking images, and the discriminator just outputs 50-50 because it can't do any better than that. It says, well, everything looks like a real image that you generate. Real images look like real images. So it's a 50-50 chance, whatever you presented with, that it's a real image versus fake. There's an objective that you can optimize to do this. So what's interesting about this is that this allows to generate images that are quite realistic, more realistic than any other approach out there so far. Underneath, the neural net can be quite complex. I mean, I drew this as a very simple graph. Underneath, there could be many convolutional layers that map from the code all the way to what ultimately become the pixels. And what you get is something that looks like this. You can try to distinguish left or right, which one is real, which one is fake. In this case, the left one is real, the right one is fake. And if you look carefully, you can see that. But it's actually quite surprising how all this works. And some recent results, like the plug-and-play generative networks that just came out just a couple months ago, make it even more realistic than what you're seeing here. But if you look at this, it's not clear how to use this to speed up learning. Because all it does, it gives you a way to generate images. The reason people typically would do unsupervised learning is because you say, well, if you know how to create something, then that means that you understand it better. But the question is, okay, well, so this thing now knows how to create images that look somewhat realistic. Maybe it understands something better, but how do we somehow pull that out and use it for something else? One way to do it would be to try to make the code, the noise into something more meaningful, which we'll call code rather than just noise. Because if you can do that, if you can generate images where this, what you feed in, has some meaning, and as you vary the code, you get meaningful variation in your images, then that means that now you can, for images, potentially backtrack, find what the code is, and then you know what the code is that corresponds to a real image, then you can now understand that there's something meaningful in that code, maybe viewpoint changes, maybe lighting changes, and so forth. The kind of things you'd hope you would understand when generating images. Simple idea that we're going to work from is that independent factors in latent code will maximally explain variations in generated images. Okay. What do I mean with that? If you have variation in your images, and you look at your code, and you want to understand where this variation comes from, if your code is higher entropy, it'll allow you to generate more variation. If you have independent variables, they will have higher entropy than correlated variables. And so if we want to maximize how much information is in our code, that corresponds to maximizing independence among the variables in our code. And if we maximize independence among those variables, the hope is that natural variation will come out, because if you have independent variables, well, let's give a counterexample. Imagine you were picked as one of your code meanings one specific pixel. If you change one specific pixel, you can't just change that. Because if you just arbitrarily change one pixel, it will not be consistent with everything else around it. And so that's not a good thing to encode in a code if you want the code to have independent factors. If you need independent factors, you need something that encodes something that you can change independent of how everything else in your image changes, like lighting would, for example, be. Formally, the way we encode this is that we want to maximize the mutual information between the code variables and the image, which you can encode in any of those two differences. We'll use the second one. It's saying we want there to be a lot of information between the code and the image. Well, the image has to be realistic, so you can't just take the bits in the code and just directly encode them in the image in a very transparent way, because then your discriminator will just say, hey, I can tell this is a fake because this is one that has the code just embedded in the image in a too obvious way. You can do some math to make this practical. If you work through the math, what comes out is that you have an objective here, which has an auxiliary distribution queue. And that auxiliary distribution effectively is like a classifier. And what you see is that, so you have an additional objective that is a classifier that is trying to recover the code from the pixels. So you were generating pixels from code, and now you want to say, I want to maximize mutual information. What that means is, from the pixel, you should still be able to know what the code was that generated those pixels. If that's the case, then there's a lot of mutual information. Intuitively, that's clear. The math also justifies it. Okay. So what that means is we can modify again, call it again then, to have an extra discriminator Q, but that's not trying to discriminate between fake or real. It's trying to discriminate which code was used to generate the image. This doesn't need to take a lot of extra work. You can actually have a shared covenant living there between the original discriminator and the one that discriminates for codes, and have just an extra output layer, and that's it. So minimal extra computation allows you to do this. Okay. Once you do this, you can get some pretty interesting results. So running infogan, we have 3 code variables. 1 is categorical, 2 are uniform. The code variables, the categorical one can take values from 0 through 9 or 1 through 10. This is MNIST, so there's 10 possible digits. The hope you'd have is that that code variable would correspond to which digit you're producing. We're not supervising that. We're just saying we're hoping that if we have an independent factor of variation that can take on 10 values, the most robust way for the system to communicate that independent factor of variation without revealing that it's generating a fake is by having it correspond to which digit you are generating. And on the left here, you see the results from the generator. If you look carefully, it's not perfect. We chose this to be representative. You see 50 digits being flashed. One of them is off. There's a 7 among the 9s. That's roughly what it's like, but that's pretty good because there's no supervision here. It's completely unsupervised, just having that regularization objective on information between code and pixels. If you change the uniform ones, this is what you get, so it corresponds to how the digits are slanted and how thick the pen is that's being used to write the digits. We didn't find more code variables that were equally meaningful, but those 3 are things we wish we could recover and indeed are being recovered. You can do the same thing for faces. In fact, there was some work that is with more supervision where you had data sets of faces where you knew that it was the same face over and over but different viewpoints. And what we're doing, we don't need to know that you get the same face multiple times. In fact, you don't need to get the same face multiple times. You just get a data set of faces and can get the same effect that it learns about factors of variation, for example, the viewpoint onto the face. You can do this with chairs. You can change the size or the viewpoint. Here's something with faces that's kind of intriguing. You can look at their emotion. On the left, they look less happy. On the right, they look happier. Then what you see here is variation corresponding to glasses. A rotation for this one, so the viewpoint. And then the next one is the presence or absence of glasses, where on the left, they typically don't have glasses. On the right, they do. And that's a subtle way to communicate a bit of information. So the main idea here is that somehow we encourage the code to transmit information that corresponds to natural variation, because if it wasn't natural variation, then the discriminator would pick up on it and would disclassify that as being a fake. Okay, in the remainder of time, I'm going to quickly tell you about 2 last things here: third-person perspective learning and safety. What's the idea in imitation learning? The idea in imitation learning is that, well, reinforcement learning is great. Of course, it's nice to learn from scratch, explore everything from scratch, but it's data intense, largely because a lot of things have to be tried that are useless, that are not useful. Most things are bad things, and you need to try pretty much all of them before you realize what the best thing is. If you can watch somebody do something, you can learn a lot more quickly. So there's a lot of work on first-person imitation learning where you would drive a car and the car experiences everything. You might teleoperate and it would experience everything. But that's difficult to do. It would be much nicer if you could learn from third-person demonstrations, where the robot watches things happen rather than experience them themselves. It's harder because the viewpoint will be different. If a robot has experienced something themselves, when they're doing it autonomously later, they can just match exactly what happened, try to match the pixels and everything. If they're watching somebody, they can never just hope that matching pixels will work, because the robot arm doesn't look like a human arm. And the robot's looking from here, and they were looking at the human from the outside. So it would never really match up. But that's what we're trying to do here. We would like, and as a starting point, here are some smaller examples, we would like to see demonstrations as in the top row, and then be able to execute in situations like the bottom row, where the viewpoint has changed from what it was in demonstration time. So the basic idea we're starting from is generative adversarial imitation learning. So here's the idea. When you want to learn from demonstrations, there's a lot of ways to learn. Often the most robust way to learn is to learn the objective that the person is optimizing. If you understand what they're optimizing for, then you can run your own optimizer to optimize for the same objective. So we're going to try to recover the reward function from the demonstrations rather than some direct mapping from state to action. If you want to do this, and you want to, let's say, train a deep neural net to recognize the reward function, what people are optimizing for, the best approach available to date, but there's parallel work by Jonathan Ho and Chelsea Finn, is to learn a classifier, a lot like the GAN setting. You learn a classifier to distinguish demonstrations from autonomous attempts. And you try to fool that classifier. Once you fool that classifier, you're doing as well as the demonstrator. Okay? And that's possible. That works well. But that assumes you're in first-person setting, where you can actually match things up. The third-person setting, that classifier will always win. All it has to do is understand which viewpoint it's coming from, and that's it. You're never going to be able to fool it. So there's an idea called domain confusion, developed in Trevor Darrell's group at Berkeley. Eric Cheng was the student pushing this forward. And the idea here is that rather than learning your classifier just as is, you're going to train your classifier going from pixels to a decision, but somewhere along the way, you force it to have forgotten some information. And in this case, you want it to have forgotten whether it was a third-person or a first-person viewpoint. So it's processing, and then you have an extra loss coming out that says it should be impossible to understand which viewpoint you're from. And then from that layer onwards, try to optimize to distinguish between expert and non-expert. Of course, that's tricky because the expert is in the one viewpoint and the non-expert in the other viewpoint, so these are competing objectives. To deal with the fact that they're competing, we let one objective have multiple frames. We let the objective that's trying to recover the reward function have multiple frames, so let's see the whole behavior over time, whereas the domain confusion is saying, based on a single frame, it should not be possible to understand whether it was third or first-person viewpoint. So this is what the overall architecture looks like. You would have multiple frames coming in. There would be a feature extraction happening that's all learned. After feature extraction, single frame should be indistinguishable between third and first-person viewpoint. But when you have multiple frames passed on, you should try to discriminate between expert and non-expert. That discriminator, the log of that output, is used as the reward function in a reinforcement learning algorithm, in this case TRPO, to train an expert to do well on learning to match the human demonstrator from a different viewpoint. Here are some of the learning curves as a function of iterations on the horizontal axis. Vertical axis is mean reward. Higher is better. So you know the expert reward here. In reality, you probably wouldn't, but to evaluate this, we have an expert where we know the reward function. They're optimizing it, and we learn from a third-person viewpoint and see how well we do on the actual underlying reward, and it's able to learn that. We also see that the domain confusion hovers around 50%, which is good. The classifier that's trying to distinguish between the two should be fooled, and 50% is where we want it to end up. Here's what it looks like. On the left is the demonstration. That's the video that's fed into the system. Several of those videos are fed in. And then on the right, you see the learning in action. Initially, it's not doing so well. It doesn't understand that you need to reach to that target point. But over time, it starts figuring out what the right thing is to do and matches the expert behavior. These are still toy examples, and I should also say, just like with generative adversarial networks in general, it's not easy to get these things to work because you have these competing objectives. But the hope here is that as a lot of people are working on generative adversarial networks and improving training for them, those improvements will also carry over to this and boost what's possible with this approach for third-person imitation learning. A big issue when you work with real systems and they're collecting their own data to become better at things, like in reinforcement learning, is safety. You might kill the system or some person near it, or you might damage things while you're learning. And so the question is how to deal with that. This could be in autonomous driving, robots manipulating fragile objects, robots themselves being expensive and you don't want to damage them. How do you train a robot for this kind of task? So the goal is that we want to learn a control policy that maps from raw observations to controls. It starts with no vision system at all. So there's no understanding of how to process the world. and still we wanted to learn to do things in the world. So you can't hope for too much here either. If you start with nothing, you can't hope that you're going to, be 100% safe in the safest possible way one could ever be, but we're going to go for an intermediate here. But we do want to learn a vision system and control system all in one go, say navigate a quadcopter through cluttered environments. And the policy will be some deep neural net because that's the best differentiable architecture we have available today. But we want it to be as safe as possible. Okay? So how to do reinforcement learning without destroying the robot during training using only onboard images. Unlike most quadcopter work where things are done in a Vicon room, motion capture, and so forth, none of that. Also no lasers that tell us anything about where things are. Just raw camera pixels and motor commands. That's it. So there'll be two terms in the cost. There's the task that we care about completing, and there is a collision cost. We don't want to collide because that could damage the system. The collision cost relates to the safety, but we need to learn it. We don't know when it happens, it's too late. You might have damaged your system. So the key here is to learn a model that predicts whether collision will happen or not based on the current set of pixels and a sequence of actions that we're considering. So the agent considers, what if I take this sequence of actions and I currently see this situation, am I likely to collide or not? Initially, this model will be garbage. It won't know. But the hope is that we can learn such a model that's pretty good. And if it's pretty good at that, then it can avoid collisions for us. Okay? So raw image and commanded velocities. And of course, you could search over sequences of commanded velocities, pick the one that has the lowest probability of collision and also does well on the task, take the first step, UT, and then repeat this process at time t plus 1. Okay? So here's what the full setup looks like for our approach. We have data. Assume we have some data. Initially, it'll be pretty much empty. Then we train an uncertainty-aware collision prediction model. That's key. We train a model that not only predicts collisions, but also tries to calibrate itself in terms of how well it knows whether there's going to be a collision or not. Initially, it should output something like, I have no clue whether it'll be a prediction or not because I've never seen anything, experienced anything. This will be a deep neural net that uses bootstrapping and dropout to have fairly calibrated uncertainty estimates. Then we look at a collision cost, and I'll give a little bit of detail about that soon, and we'll make it speed dependent. So that's the little thing we're going to do to allow this to work. We're going to say if we fly extremely slowly, a collision is not too bad. And so when you're very uncertain, you should decide to fly extremely slowly. You might bump into something. It's not going to kill your quadcopter, at least not if you do it once or twice. And so that's OK. Then you collect data, use that data to improve the probability of collision model, because if you collided, then you can go back and say, well, I took this sequence of actions from that observation state, so now I can improve my probability of collision model and repeat. Here is the cost function used. It's bad when you have high speed and there's a high probability of collision. Or it's not just a high probability of collision. It can also be that you're just very uncertain. There's high variance, in which case it's also bad to go at high speed. Question is how to know that there is large uncertainty. We do bootstrapping. So at training time, we'll get data, which means current image and sequence of controls, and then see if a collision happened in that period or not. So you learn from actual collisions if collisions are likely or not. You resample your data multiple times, not just 3 times. This gives you multiple models, and you can look at how well these models agree. At test time, agreement of these models will tell you something about how certain you can be about the prediction of collision. You can do the same thing in a slightly different way, which is good for smoothing this out. It misses some of the bigger patterns, but it's good at the local level. You do dropout, which is a lot like bootstrapping locally, where you just randomly remove edges and see how all these models agree at test time. Okay, let's look at a video of this. Not sure how to make that happen in the system. Not popping forward. Oh. Cursor there. So we'll watch the algorithm I just described in action. So there are several starting locations. From all 4, it starts 5 times. This is what the quadcopter sees. There are 2 learning algorithms running. I mean, there were 2 learning algorithms run separately. We're showing videos of both of them. One of them ignores the uncertainty estimates and just uses probability of collision, which means initially it's not great because it doesn't understand. And so the thing to look at is the top histograms. On the left, it doesn't account for its own uncertainty. It doesn't even estimate it. You see there's a lot of collisions at high speed because it doesn't understand that those things might happen. On the right, this doesn't happen. There's still a few high-speed collisions, meaning that the uncertainty estimates are not perfectly calibrated. There is some issues with them, but they're pretty good. It's definitely making it behave a lot better than if you completely ignore it. And so in a relatively small amount of time, it's able to learn a vision system for this quadcopter to navigate around obstacles. We've done the same thing in an RC car to navigate in hallways, and we're trying to now scale this up. The bigger vision here is that if we want to have really good vision-based flight, we need these quadcopters to do autonomous data collection. And this is a way to enable autonomous data collection in a way that you could just, in principle, let go of a few hundred of these, let them go out, all collect data, all explore relatively safely because they understand when they might collide in a bad way, and learn from that, share the model, and do really, really well. So here's the RC car experiment. We just put an obstacle in front of it and had it learn, but also there's obstacles on the side. And it then, for each one of them, estimates the probability of collision, takes into account uncertainty, and then initially, of course, it doesn't do too well, but over time, it gets better at understanding when there's high probability of collision versus low probability of collision, and learns from scratch a navigation system. This has to be scaled up a lot to be practical, but this is just a proof of concept that this seems quite possible to learn from completely from scratch. Okay, that was safety. If you want to try out some of those things, and you don't want to code everything from scratch, I mean, it's good learning experience to code from scratch, but if you want to at least look at an implementation that's quite refined, you might want to check out RL Lab. It's an open source implementation of almost all the state-of-the-art reinforcement learning algorithms, and available for any kind of use, research, but also commercial use and so forth. I should say, available for free for all those kind of uses. What are some of the frontiers we're pushing right now? A big one is shared learning. Everything I've shown to you is kind of exciting because the system is learning from scratch. It's kind of sad. It has to learn from scratch every time. Why is it not using what it learned previously to learn more quickly on the next thing? Why is it not learning more quickly to, let's say, screw a cap into a bottle once it's learned to stack a Lego block? Well, right now, that's not really happening. And once that can be made to happen, it'll be much more efficient to acquire a large range of skills. So that's a very important area of work. There is some work going in this direction. There isn't anything that really has made a major breakthrough yet. Everything I've shown to you is reactive, except for the recurrent neural net that learns the algorithm, but then ultimately still it's reactive. But almost everything I showed you is reactive, and it goes from pixels to actions. That's not good enough in many situations. I'm giving a presentation here, but when I'm looking that way, I still know everybody's here. My actions are according to that. For that, you need memory. You need an internal feedback loop with storage that remembers things from the past and remembers not just everything, or if it remembers everything, it needs a really good indexing mechanism, or maybe a really good decision on what to remember and then use that. You also probably need memory for thinking ahead. Everything that I showed you works at a very low level, pixels to torques. But it's not how humans make decisions. It's a very ineffective way to make decisions. When this morning you woke up and you decided what to do, you didn't think about every step you're going to make during the day. That would be totally stupid. But that's effectively how these algorithms are all reasoning. They're all thinking at that lowest level at all times. So So you need abstractions. You need to think about things like, okay, maybe I'll, catch up on email, and then I'll meet with this person, I'll go to a presentation, have food, and that's the level at which maybe you plan out your day. The challenge here is, how do you build a system that can reason at that level, but in a way that's still connected to the lower level, that is meaningful? It's very easy to just define some abstractions and say, if you're in a meeting, you can have learned something, and if you eat, you might not be hungry afterwards. But what does that mean then at the low level? Making that connection, making that grounding is really, really hard. Same thing we need grounding for. Another thing we need grounding for is language. If you want to tell a robot what to do, that's going to be even more convenient than always having to show it. It's great if we can do third-person imitation. It's even great if we can just ask it to do something and we'd understand what you mean. Most work on natural language processing is in understanding statistical patterns. Which word comes after which word? If there's a sentence in English, what's the corresponding sentence in Chinese? If there's a question, what's the typical answer? But imagine you just build a system that says, you ask it, hey, please bring me a cup of coffee. And it says, sure, I'd love to bring you a cup of coffee. Statistically speaking, that's a great answer. But if the system actually doesn't act on it and doesn't grab the cup of coffee, it's totally meaningless. And so you need to ground what's the natural thing to say into what the actual actions are that correspond to this. This is a longer term thing, but we're already thinking about it now. The question is, what if we are successful? What if we do build an amazing reinforcement learning agent? It's so good. Whatever reward function you specify for it, it'll learn against it so quickly, it'll optimize it perfectly. Okay, let's assume that happens. Now you say, oh, robot, tomorrow morning, please give me a cup of coffee. Get it ready for when I get out of bed. Seems like a good thing. Okay, the robot says, okay, my reward is getting you coffee in the morning. No problem. I'm really good at maximizing your reward. I'll take care of it. But now maybe you live with somebody else. They want a cup of coffee today. Well, what should the robot do? Well, it's possible if they make themselves a cup of coffee that they make it run out of beans or run out of water, or maybe they break something. So the optimal strategy for the robot is to prevent that from happening and not let anybody use the machine. That's not what you want, hopefully. So what do you want? You want something a lot more complicated. And it's very hard to specify what you actually want. Think about tax law. In some sense, that's people trying to specify how taxes should be paid. But then there's a whole other group of people who figures out how to not pay taxes, and they always tend to succeed, it seems, if they spend enough effort. And so what that shows is that even when people put enormous amounts of effort into specifying what they want, there are always loopholes. There's always things that you didn't anticipate that somehow give you an outcome you didn't want. And so what we really want is a robot that understands our values and then aligns their values with ours and acts according to them. A very simple starting point. So this might sound very abstract, but a very simple starting point could be, what if you do research on, there are 2 videos, short video clips, 10 seconds each, of a person one time, another time, same person. The person labels it. This was a happier 10-second period in my life than this other one. Can you train a system to actually match up with that and understand when a person was happier versus less happy? If that becomes possible, that would get us closer to value alignment. A lot of things we're looking at in our work is how to interpret specifications of reward functions as noisy observations of a reward function rather than the actual reward function, and how to do inference against this noisy observation that could be in terms of numbers, language, and so forth. One of the things I'm most excited about these days is that because of the way the machinery has been changing, and a lot of it is the same machinery no matter what problem you're attacking, in fact, a lot of it invented here at Toronto, you can tackle a lot of robotics problems with the same ideas. Whether you're interested in manipulation, locomotion, driving, or flight, you can think about the same technical problems and make progress on all of them at the same time. Thank you.
The algorithm on the RC car, what were the inputs?
So for the RC car, the inputs were forward velocity. You could choose and steering. you could not decide to go backwards. Something we're looking at in going forward is see if, so a good strategy here would be to also maybe make a 3-point turn, to be able to turn away from obstacles when you're really facing a wall or you're going in the wrong direction, things like that. We're very curious if that would be possible to learn and how much data it would take. But for now, it's just adjusting forward speed and steering angle.
The video.
On the other end is just raw pixels. It's not at the resolution you were seeing. I think it was at 32 by 32 is what the input images were. And then there's a convnet sitting behind that maps to probability of collision. So it takes in, the convnet takes in images. Then there's a separate input for sequence of controls you'll apply in the next few time steps. And then based on the combination of current image and sequence of controls you're considering applying, it'll output a probability of collision. Yes?
The same for every iteration in each case. So how are you certain not just, I guess, Jack coaching where you could, for example, yeah, that's the question.
So for the RC car, the video I showed you was starting essentially in the same spot. For the quad, it was starting in 4 different locations. So you could wonder if it's memorizing strategies for those 4 locations. The way we've tested that is the student would wear safety goggles, and we really should have recorded that. But the student would stand in front of the quad. This is when a funding agency came by and wanted to show, we need more funding. We're doing good stuff. And so the student wore safety goggles, stood in front of the quad, and then the quad indeed avoided the student. But I think the higher level question here is really, it's really just a proof of concept. It's one obstacle that you steer to the left or the right of. You were not allowed to go up or down. You had to go keep same altitude, go left or right or forward, and adjust speed. And so this is very limited. In terms of visual representation, you need to learn about what maybe some darker object looks like in the middle, and then some brighter stuffs on the sides, and the brighter stuff might be better to go towards. It's not hard-coded, but I don't think it's pattern recognition-wise the most complicated problem. And so a lot of our effort now is into how to scale this up, because I think if we want to do this, one way to do it is to just say, hey, we're just going to pre-train on ImageNet or something like that, and then we don't need to train as much anymore on this kind of problem. Maybe we could go to more complicated scenarios very quickly. But the other route, the one I'm personally most excited about, is to see if we can continue to train from scratch, potentially even recover visual features that are interesting more generally than just for collision avoidance, though it might be a little tailored to that, by scaling it up and getting a lot of data with quads, visiting a lot of environments. Or RC cars is actually what we're mostly looking at, because of all the regulations, it's harder to fly quads in many places. It's easier to just have a lot of RC cars go around campus and go around buildings.
So you could use GKG, right?
So yeah, so we've been looking at that a little bit. There's also a recent result by Ferrishtay and Sergey Levin at Berkeley that actually looked at quad flight in simulated environments where they never used a real image, but what's really surprising is they didn't even use realistic renderings. They just rendered in very naive ways. They would render they would generate reasonably set up geometric environments and then just put textures on every surface, and a lot of random textures. Not random in terms of a Gaussian noise pattern, but have a lot of different textures that are meaningful textures randomly placed on each surface. And if you train long enough in simulation, it seems to recover something about where the deepest point is in the image and be able to continue to go towards open space in the image, in the real world, even with zero training data from the real world. So I think that's very surprising, because it suggests that maybe realistic rendering is not even needed. You can do much cheaper, much faster rendering than GTA 5 would provide. Yes?
You mentioned that you recovered some uncertainty estimates using Dropout and Bootstrapping and some of the collision avoidance work. I'm wondering if you've explored getting principal uncertainty estimates in other neural network-based work, And do you think this is going to be a crucial component as we integrate some of these systems into realistic robotics systems and other types of systems?
So there is some work, often under the name Bayesian neural networks, and Yaron Gal and Zubin Garamani have pushed a lot of that, and some of our work is largely inspired by some of the things they've been doing. So there's definitely a lot of work that tries to get this to work, get calibrated estimates. In terms of importance, I think it's going to be critical for these kind of systems that take actions with consequences, where it's not just about classification accuracy, it's also about certain actions are worse if you take them, if they're wrong, than other ones. And to understand when you don't understand and then fall back on either a human controller or a fallback policy like just hovering in place or something. I think one part is for the system to understand when it doesn't understand. I think that'll be critical. A very related problem that I think is very exciting is thinking about mining difficult scenarios. So in computer vision, people have done this for a long time, where they would retrain on the examples where you do the poorest, because they have the most information about what you still have to learn. But the question is, can you do something like that in reinforcement learning, where you're acting over time? And so it could be more difficult to put you in a difficult situation, and it needs to be the right kind of difficult situation, and how to make that work. One example is AlphaGo. AlphaGo plays against itself, but also past versions of itself. And effectively, these past versions are also are trying to find ways to beat it. And by playing against things that try to beat it, if it has a weakness, then that weakness would be exploited. And now it could learn from that and patch that weakness. And so the question there is, can we do this for something like self-driving cars, where humans have collisions every 3 million, like big collisions every 3 million miles, which is very far apart. Once you have a self-driving car that only collides every 1 million miles, naively collecting data on policy, the policy it has right now, and tries to improve that policy incrementally, the data you collect that way will be not very informative for learning, because most of the time will be things you already know. The updates will do nothing for you. And so how to do that, I think, is really, really interesting. Another issue that comes up is if you do things like reward function learning and value alignment, if you naively learn a reward function without bootstrapping, without any uncertainty estimates, almost always there will be holes, meaning there will be parts of the space where reward is really, really good. It's part of the space you never saw, but the neural net will do some arbitrary things in that part of the space. And so if all you do is just train it naively and then optimize against what you just learned, it's guaranteed to do something that you didn't want it to do and find one of those holes where it can really do well, according to this objective that it's optimizing but actually be bad in practice. Angela.
The last question.
I have a question around systematic. You talk about pixel to action, and the last examples there are a lot of low-level components acting, and you operate your learning. And obviously, if you do generic pixel to action, that's the most generic, that's really how it disadvantages. But just, what your thoughts are about kind of architecting a system that maybe possible is responsible, or you get intermediate outputs.
So let's see. I think there's a range of answers here. So going all the way from pixels to actions is great because you don't lose anything. You keep the flexibility to be optimal. Once you constrain it anywhere along the way, you might lose optimality. And so it'll depend a lot on how much you know about how you're constraining it, and how much you might be losing things when you're constraining it. So, for example, for the PR2 robot, when it's learning manipulation, you could say, oh, this is just about understanding a position you need to go to and getting it into position. But when we try to control it at a position level, it's actually very hard to get this to work. Because it turns out that feeling out the contact and understanding to be compliant and pushing against things really helps. You don't want to do this just vision to location. You want to do vision to torques that feel things out. So there it's really going from low-level perception to low-level action. For the driving, there's effectively a PID controller running. You ask for a velocity, and that velocity, there's some controller on the motor that makes sure that you get that velocity. Same for steering. You don't apply some current to the motor, you actually choose a steering angle or a change in steering angle, and there's a little feedback loop making that happen. And we haven't tried it without it. I think it would work worse without it, because I don't think we lose anything by having that abstraction. And it gives us a good representation that we know is useful for actions that if we didn't put it in there, we might want it to emerge anyway. And so I think whenever you know something you want to have it emerge anyway, and you know how to put it in, it's not a bad idea. I think one interesting intermediate is to try to put in conceptual knowledge. So if you say we're going to use an LQR controller, like the embed to control, we're going to put in a value iteration network, then you're essentially putting in the conceptual knowledge of what a planner should do without constraining it all the way to make a plan against a very specific model. And so I think for now it really depends on what situation you're in. I think related also, pixel to action does not understand objects. It just, like, it's all the same. Like, there's features, and features lead to actions, and those features are learned. But it could be that if it actually really knew what objects were somewhere along the way, just like you have a value iteration network, maybe you have a object notion somewhere, and then it's supposed to reason based on these objects that emerge from the visual processing. Maybe it would be more robust, because it seems meaningful to act based on objects rather than based on just features. And so I think there's a lot of ideas in the kind of intermediate regime that are very interesting to explore and see what happens.
All right, well, let's thank Pieter for a very